Welcome, Mr. Sutton here with the BC Calculus 710 Part 2 homework solutions on the alternating series test. For this problem, we're trying to figure out whether or not this series converges. Now, we do have an alternating series here, so alternating series test seems like it would be a good one. But is this decreasing in absolute value to 0? I think it's decreasing because we have this higher exponent in the denominator, but is this going to 0? Let's try taking the limit of this thing as n approaches infinity. So if we do that, I can start by simplifying this denominator logarithm. I can pop this 2 out. And now I can actually, as n approaches infinity, cancel these ln of n's out. So this just ends up being plus or minus 1/2. Now this is not 0. So our series is not decreasing in value to 0. That means that this is actually going to diverge by the nth term test. On this problem, we want to know which of these statements is true about this series. So first statement, the series is alternating. Well, it certainly looks like it's alternating with this -1 to the n term in the numerator, but how about in the denominator? Because alternating means you're going positive to negative, but whether or not you're positive to negative is determined by both of these things. Well, if we're greater than 2, greater than or equal to 2, in the numerator then we're going to have the square root of 2 and then plus or minus a 1. Now, the square root of 2 is bigger than 1, so you're always going to get something positive in the denominator. Since you're always getting a positive in the denominator, it's just the numerator that's really determining your sign. So we are going to be alternating with this -1 to the n upstairs. So statement 1 actually ends up being true. Okay, so anything that doesn't have 1 in it is out, like choice A. Everything else has 1 though, so we keep going. This next one, they're saying the n plus 1th term is less than or equal to the nth term for all n greater than or equal to 2. Well, we have this n in the denominator that's growing, so that would seem like we're getting smaller and smaller for our fraction. But we also have this -1 that's flipping back and forth between negative and positive. So that may do some strange things. So I think it would be a good idea to test out some n values and make sure this is actually true. Let's try out just the n value 3 and 2, right? The third term versus the second term. So we've got -1 to the 3 over radical 3 plus -1 to the 3. And we're trying to figure out if that is less than or equal to all of this stuff with 2 plugged in. And we're doing absolute value, so we don't have to worry about this -1 upstairs. But downstairs, we do have to worry about this -1 to the n because this whole denominator may or may not be positive or negative depending on the interaction between these things. We can't just make this positive like we can the numerator. So I'll have 1 over square root of 2 plus -1 squared. And let me just do this on the calculator to see if these come out to the same thing. This actually is a calculator question. So let's try out this left one first. We've got 1 over radical 3 plus -1 to the third comes out to about 1.366. And then let me try it again with 2 instead of 3 in all those spots. So we've got a 2, then we've got a 3, or a 2 over here rather. It's about 0.414. So we have 1.36 versus 0.414. Is the thing on the left less than or equal to the thing on the right? Not so much. So this one we disproved with just one counterexample. So anything with 2 in it is gone. So that narrows it down to choices B and D. Now this last one's a little bit easier to check. They're saying the limit of this expression here is 0 as n approaches infinity. Well, as n approaches infinity, we can forget about this -1 to the n, because it changes back and forth between negative and positive 1, but this other term here that's growing to infinity far outpaces it. So we can really just call this -1 to the n over radical n. And this is just going to become plus or minus, well actually this is going to 0, right? Because your denominator is growing faster than your numerator. So that actually turns out to be true, which is going to be, let's see, choices, we want 1 and 3 as true, so that would be choice D. On this problem, we want to know which of the following series are conditionally convergent. So that means they converge without absolute value only. So we'll start by figuring out which of them converge just with this alternating going on. Now we notice that all of these terms have denominators that are growing faster than the numerators, and we have alternating on all of them. So these all alternate and decrease in absolute value to 0, which means that they will all converge without absolute value. So really we just need to figure out which one of these do not converge with absolute value thrown in. So let's check them out. This first one without the absolute value, or with the absolute value rather, is going to be just 1 over n. Now this is the harmonic series, which we know diverges. So that means that 1 converges conditionally. Next, option 2, this is 1 over n cubed. This is a p-series with a p-value of 3. Since that's greater than 1, this converges absolutely by the p-series test. So choice 2 is not the answer we want because we want conditionally convergent, not absolutely. Next, choice 3, this is really 1 over radical n with the absolute value thrown in there. So this is going to be another p-series with a p-value of 1/2 for that radical. Since that's less than or equal to 1, this diverges by the p-series test. So this means that only options 1 and 3 converge without absolute value, which means they are both conditionally convergent. So that means we're going to pick answer choice C. For number 10, we're given a power series that converges conditionally at x equals 5. We want to know which statement about convergence at x equals -4 is true. So it could either be absolute convergence, conditional, divergence, or there's always D, not enough information to tell. So how do we figure this out? So first thing to recognize is that this series is centered at x equals 1. So there's some radius of convergence that tells us how far to go from 1 in each direction to get the endpoints of convergence. So the next clue they gave us was that we're converging conditionally at x equals 5. What they're basically saying is that x equals 5, since it's converging conditionally there, 5 is going to be one of the endpoints. It converges absolutely between the endpoints. It's only at the endpoints that you can have this conditional convergence. It might be absolute convergence there, but if it's conditional, it's definitely an endpoint. Okay, so that means that our radius of convergence is just the distance from 1 to 5, which is 4. So we can actually use this to write the interval of convergence. So that's going to be 1 minus 4 to 1 plus 4. So we're going from -3 to +5. Yep, change this from a 5 to a 4. There we go. -3 to +5. All right, so let's take a look now at -4. Since this is the interval of convergence, we're not really sure about what's going on at either of these endpoints, whether it's converging or diverging. But one thing we do know for sure is that anything outside this interval is going to diverge. So since we're diverging outside this interval, for example, at x equals -4, we can say that we're diverging at x equals -4 for a certainty. So that would be choice C. Now these other options here, converging absolutely or conditionally at x equals -4, obviously that's the opposite of diverging, and there is enough information as we showed here. For number 11, they're asking the alternating series test can be used to show convergence at which of the following alternating series. So we're given 3 options here, and it might be some combination or just one of them. So let's take a look at each of these. So remember, the alternating series test, you need to be alternating, which all of these appear to be. You also need terms that are decreasing in absolute value to 0. So that's the big test for all of these. Are we decreasing in absolute value to 0? Taking a look at this first one, so we're decreasing, not decreasing anymore, decreasing, not decreasing anymore. So this is an issue, right? These terms are not always getting smaller. In fact, there's almost a pattern to the way in which they are not getting smaller. So this first one is a big no because we're not even decreasing consistently. Okay, let's take a look at the next one. So these terms appear to be decreasing, and if you look at the nth term, they definitely are decreasing continuously. You just keep getting bigger in the denominator. We also can say that the limit of 1 over n, the absolute value limit here, is going to 0. The nth term is going to 0. So this one is indeed going to be provable as converging by the alternating series test. That leaves us now with the third option to look at. Now looking at the answer choices, if 2 is the answer, then the only options were either 1 and 2, 1, 2, and 3, or just 2 by itself. There's not an option for 2 and 3. So actually at this point you could go ahead and pick choice B right away. But let's just take a look at the third one and see why 3 is not a good option. So these are decreasing in value as you go. However, if you take the limit of the nth term, that's going to be 1 over 2. So although this is decreasing in absolute value, it's not decreasing to 0. So this actually fails the nth term test, and we can't pick this as an answer for alternating series test. So at the end of the day then, only choice B for option 2 is the one that the AST can prove converges. For this problem, we want to know all the values of x for which this series converges, so the interval of convergence. Since this is not geometric, we use the ratio test to figure out the thing that we're setting less than 1. So I have my n plus 1th term, which is going to be x minus 1 to the n plus 1 over n plus 1. And we're taking the limit as n approaches infinity of this n plus 1th term over the nth term, x minus 1 to the n over n. Same change flip. We've got x minus 1 to the n plus 1 times the n that flips up from the denominator. In the denominator of my big fraction now, I've got an n plus 1 and an x minus 1 to the n. Can't do anything yet about the n plus 1s, but let me reduce these x minus 1s. Using my exponent rules, I can subtract the exponents. So this is just going to be x minus 1 to the first power and an n left in the numerator. This x minus 1 to the n cancels out down here, so we just have n plus 1. Now, as n approaches infinity, this plus 1 goes away, so you just have n over n, which is just 1. And we still have this x minus 1, which is treated as a constant, just hanging out in the numerator. So that's what's left inside my absolute value. I will now set that less than 1, and that'll be where I get my initial interval of convergence from. So I can rewrite this without absolute value as negative 1 less than x minus 1 less than 1. Adding 1 to all three sides here, we end up with 0 less than x less than 2. But I'll put a question mark because we're not really sure if those are the true interval here. We have to test the endpoints of 0 and 2. So if x is 0, then plugging 0 in up here, that's going to be negative 1 to the n over n. Now this is the alternating harmonic series, which if you recognize that, you know this automatically is shown to converge, automatically converges. So now we move on to the other endpoint of 2. If x equals 2, we've got 2 minus 1 to the n, which is just 1 to the n, which is just 1 over n. Well, this is the harmonic series, which is known to diverge. So writing our final interval of convergence, we can write 0 less than or equal to x less than 2, and that's going to give us choice D. For this problem, they're telling us the limit as n approaches infinity of a sub n, so some term is approaching infinity, and then the n plus 1th term is bigger than or equal to the nth term. So there's a few facts that come out of this that are going to help us decipher these answer choices about converging and diverging. One of them is if we have the n plus 1th term of this being greater than the nth term, that means if I turn these into fractions and do 1 over a sub n plus 1, that's going to have to be less than or equal to 1 over a sub n. If this term is bigger than this term, bigger denominator here means a smaller fraction than this one. Okay, and another important fact here is if the limit of this thing is approaching infinity, 1 over this thing as n approaches infinity must be approaching 0. So all of this is to say that we have terms, if we have 1 over a sub n, like we do in answer choices C and D, then we have a term that is decreasing in absolute value to 0. So that might be important. Now let's go through these answer choices. So answer choice A, 1 over a sub n diverges. Well, this may or may not be true, but we can find a counterexample. Let's say we had 1 over n squared. 1 over n squared is a p-series of 2 that converges, not diverges. So that's going to be no for answer choice A. For answer choice B, we have an alternating version of this term that's going to infinity, and they're saying that converges. Well, This one's pretty easy to disprove. If we take the limit of this thing as n approaches infinity, this is going to be plus or minus infinity, which is not 0. So that's going to fail by the nth term test. Okay, choice C, 1 over a sub n converges. Well, we can find an easy counterexample there. 1 over n limit would be 0, but 1 over n diverges. The harmonic series diverges. So we can actually eliminate choices A, B, and C pretty quickly. Now for choice D. Well, choice D, we have an alternating series here that is decreasing in absolute value to 0. We've established that up here. So since we're alternating and decreasing in absolute value to 0, the alternating series test says that, yes, this is going to converge. So choice D, then, is what we're looking for. For number 8, we want to know all the values of x for which this series converges. So we're essentially asking for the interval of convergence, and here are the options here. So let's go ahead and do our ratio test, since this is not a geometric series because of this n down here ruining it. So we'll do the limit as n approaches infinity of the absolute value of the n plus 1th term over the nth term. So let me just write it all out, and then we'll go through it. So here it all is. Here's the n plus 1th term in this top fraction. We have x plus 3 halves to the n plus 1, and this n is in the denominator, so we've got n plus 1 there. And down below we've just got basically this in fraction form, the nth term. All right, let's multiply by the reciprocal now. So we've got x plus 3 halves to the n plus 1 times n all over n plus 1 times x plus 3 to the nth power. Let's reduce as much as we can now. These exponential terms can reduce a little bit, leaving us with an x plus 3 halves to the first power on top, and everything else is essentially unchanged. So as n approaches infinity, we've basically got n over n with a coefficient of x plus 3 halves. So this just reduces then to the absolute value of x plus 3 over 2. Now by the ratio test, we have to let this be less than 1. And let's just rewrite this as negative 1 less than x plus 3 halves less than 1 to get rid of that absolute value. Now we just subtract 3 halves from everywhere. That gives us negative 5 halves less than x less than negative 1 half. So this is our kind of our rough draft of the interval of convergence, and it narrows it down to choices A, C, or A, B, and C. D and E are out of the running, so it's A, B, or C. We know that at the very least these are the numbers, but we don't know about the endpoints, whether they converge or not. So we need to plug in negative 5 halves and negative 1 half to the original series to figure out if it converges. So plugging in negative 5 halves, what happens if we do that? Negative 5 over 2 plus 3 over 2 is just negative 2 over 2, or negative 1. So we've got negative 1 to the n times another negative 1 to the n. Well, that's just going to be negative 1 to the 2n, which is always going to come out to positive 1. So after all that craziness, plugging in negative 5 over 2, we just have 1 over n as the actual series when all is said and done. Well, this should look familiar. This is the harmonic series, and we know that this diverges. So we know that we have to keep the less than with no equals for the negative 5 halves. Okay, we still have to try out the negative 1 half. If I plug that in, well, now I've got, this will be, let's see, 2 over 2 to the n, so 1 to the n times negative 1 to the n. This ends up then being just negative 1 to the n over n when all is said and done. This is the alternating harmonic series, which we know converges. So our final draft of our interval of convergence is going to then be negative 5 halves less than x less than or equal to negative 1 half, because this endpoint converged. And that is going to give us choice B. For number 15, we're given a Maclaurin series for a function f as shown below here. And the first thing they want us to do is find the interval of convergence and justify the answer. This is not a geometric series, so that means we're going to have to use the ratio test. So I'm going to take the limit as n approaches infinity of the absolute value of the n plus 1th version of this over the nth term. So let me just write that out, and then we'll see how things come together here. So here's my n plus 1th version of my nth term. So I'm going to have 2x to the n plus 1, so n plus 2. And we've got n plus 1 down here, so again n plus 2. Lower fraction is just the exact nth term. Let's go ahead and multiply by the reciprocal now to simplify this. So I've got 2x quantity to the n plus 2 times n plus 1 over, in the denominator now, I've got n plus 2 and this 2x to the n plus 1. Can't do anything with these n plus 1s and 2s just yet, but I can do something with these exponentials. If I subtract my exponents, I end up with just 2x to the first power in the numerator, along with the n plus 1, and now we have the n plus 2 down here. As n approaches infinity, these n terms are going to go to 1, leaving us with just the absolute value of 2x. So by the ratio test, we let this be less than 1, which means that absolute value of x is going to be less than 1/2. Which means, if we get rid of that absolute value, that negative 1/2 is less than x, which is less than 1/2. So this is our rough draft of our interval of convergence. We do still need to test both of these endpoints. Testing out negative 1/2, if we plug that in, this is going to be negative 1 to the n plus 1 over n plus 1. Now this one is alternating. We can see very easily that these terms alternate and decrease in absolute value to 0. The denominator keeps getting bigger and bigger, so the whole thing is decreasing, and the limit of the nth term will be 0. So that means that we're converging by the alternating series test for this branch. Now we have to do the other branch where we plug in 1/2. So at 1/2, we're just going to have 1 to the n plus 1, which is just 1. So this is 1 over n plus 1. Now this one, if you look at where we're starting at n equals 0. So we're doing 1 over 1, so that's just 1, plus 1 over 2, plus 1 over 3, plus 1 over 4. This is actually the harmonic series. It just isn't as obvious as if I wrote 1 over n. So that means that this is automatically going to diverge. So we converged at negative 1/2, diverged at positive 1/2. Our final interval of convergence then is going to be negative 1/2 less than or equal to x less than 1/2. For part B, they want us to find the first 4 terms in general term for the Maclaurin series for f prime of x. So the process here is pretty straightforward. You just have to take the derivative of the first 4 terms and the general term. You've got to be careful on this last one, we'll see in a sec, but let's start at the beginning. So derivative of 2x is 2. Derivative of this next one, we're going to have 2 times this fraction, which is going to cancel out the 2's, leaving us with just 4x. Next, we're going to have these 3's canceling out, leaving us with 8x squared. And after that, we're going to have these 4's canceling, leaving us with 16x to the third. Over here for the nth term, n plus 1 and n plus 1 are going to cancel, leaving us with 2x to the n times, now we got to be careful, we have an inner function of 2x times 2. So be careful with that last chain rule. That's probably where a lot of people are going to lose points on this one. For part C, they want us to use our Maclaurin series that we found in part B, which I've rewritten below here, to find the value of f prime of negative 1/3. So you basically have to plug negative 1/3 into this infinite series, which makes things difficult. The key to this is recognizing that if you look from term to term, this is a geometric series. We have an a1 of 2, and we have a common ratio of 2x. We're multiplying by 2x each time to get the next term. So I'm first going to put this in infinite geometric sum format. So we, in general, have a1 over 1 minus r. In this case, then, that's going to be 2 over 1 minus the r value of 2x. And when I've written it this way, this is very finite looking. I just have to plug negative 1/3 in for x here. So let's go ahead and do that. And this is actually good as a final answer. This is numerically equivalent to whatever answer it is they're looking for. So really any simplifying you do at this point is at your own risk. But I'm going to simplify just because I like simplifying and I'm not actually taking the AP test right this second. So this is going to be 1 plus 2/3. So 3/3 plus 2/3 is 5/3 down there. And if we multiply by the reciprocal now, we've got 2 times 3 over 5, which is going to be 6 over 5 for our final simplified answer.